PolySense is a fabrication process that adds electrical functionality to various materials. You can create clothes which measure your body movement, provide heat in the cold, or even track your motion for VR or light and sound control.
Our next talk is about fabric augmentation using tools you can find in any kitchen.
We present Cedric Honnet with PolySense, reverse engineering flex sensors and destroying your kitchen with chemistry for electrical functionalization of everyday objects.
Hi everyone, my name is Cedric, and along with Olivia, we're going to present PolySense, an accessible process that makes fabrics smarter. Okay, so this presentation will be chronological from the original problem to first solutions that we found, followed by a few unexpected discoveries and opportunities for the future. Let's start with the initial motivation. So this project was born at DataPolet, a hackerspace collective focused on e-textiles, such as this matrix pressure sensor. So this particular sensor uses two kinds of materials. Let's discuss first the conductive fabric. So on the right, we can see horizontal stripes used to sequentially power the sensor for rasterization when we read the sensor. On the left, we can see vertical stripes that are connected to the analog input of the Arduino with a bit of passives to pre-process the signal. And the Arduino reports the signal to the computer. And in the middle, you can see a darker fabric. This is the piezoresistive material. It changes its resistance when you press it. This material is expensive. It's about $200 per square meter. And it became harder to get over time. So what's this piezoresistivity anyway? One of our co-authors on this project, Hannah Wilson, maybe some of you met her last year. She was giving a couple of sessions on e-textiles. She did this really cool visualization of what's happening inside. So we illustrate it here as a layer of conductive particles, all those black dots. But I think it's better to see it as fibers that were cut. And it's like a perpendicular visualization of the fabric. So when those are pressed together, the overall conductance increases because each of them is poorly conductive, but still conductive. So the fact that the conductance increases, it makes complementary behavior in the resistance. So the resistance decreases when you press it. And we can measure that with the Arduino. So we tried to make our own coating ink with silver, copper, carbon particles, and we really never got anything that would work. Either it would oxidize or it would not conduct at all. It's actually a difficult challenge. It was difficult. So we realized that we didn't really understand the material. And fortunately, I made a friend who's a collaborator on that project too, Anna Batista from Lisbon. And I spent a week in her material science lab. And after a few analyses, including Raman Spectroscopy, we understood better what could be in this reference material. So the Raman Spectroscopy tool looks a lot like a laser, but it's actually much smarter than that. What's happening inside is that so it looks like a microscope, and it has a laser that shoots light in whatever you're observing, and it looks at what is coming back. The light is pulsed at a certain frequency. It's actually a swipe frequency, and you can see what comes back a bit like. Let's try with that. If you think about it on the acoustic domain, when you knock on that, okay, maybe the sound is coming from here. You can hear a specific acoustic signature And when you knock on something else, I don't know, like my phone, you can hear a different kind of sound. And this can be represented as a spectrogram. Well, this tool that I'm showing on the screen is doing the same, but instead of sending an acoustic impulse, it sends an optical impulse. And we can see at the bottom right some spectrograms that are representing the materials that we're observing. So with the software, you can point at the specific part of the material that you want to observe, and it will tell you something like, this looks like carbon, graphite, PSS, or many other kinds of materials. And in our case, it's another one that I'm going to discuss. So thanks to the expertise of those friends, we found various ways to replicate this amazing sensor that has this piezoresistive behavior. And we really worked hard to design a simple process that you can replicate in your kitchen. So you don't need this mad tool that you can see on the screen. We found this simple approach that only uses two chemicals. One is called pyrrole. It's a monomer, and I'll explain a bit later what are those things, what are their functions and what are their behavior. And the other is iron chloride. It's a fairly common chemical that is used in to make PCBs. So when you make a printed circuit board, like the classic Arduino or whatever, you start from a plate of copper and you etch it with this thing, most of the time iron chloride or perchloride. It has several names. Anyway, it's fairly common, it's fairly cheap. So we use the magnetic stirrer, you can see at the bottom left. But you could use whatever you want, a washing machine, a tool to... A blender, thank you. A tool to make your batter, anything. Not the blender that would make juice though, because you would destroy your... yeah, the hand mixer? Hand mixer. So yeah, you can mix it with whatever you want. And we obtain a pressure sensor in about 1 hour with all of the setup included. So you can see at the bottom right, the first test that we did. So we dried the textile and we just measured the Z pressure, so the pressure between the bottom and the top. But we can measure the pressure, the resistance in different ways. So let's talk a bit about applications. Here's one of the applications that we did. We'll demonstrate one of them with Olivia at the end. But this one is basically an off-the-shelf glove that we functionalized. And you'll see how you can functionalize materials in a few seconds. But basically, you take this thing and you kind of dye it. It's a molecular level dye. And in this case, we can measure when fingers are flexed, or the pressure at the intersection. And we apply it to a virtual reality hand. So you can imagine some kind of motion capture tools. And as for all of our projects, this one is open source. And you'll see the GitHub repository at the end and in most of the slides here. So for another conference called Augmented Humans, we presented this project, which is using off-the-shelf kinesio tape. I actually have it here. So this tape, let me see if I have it. Yeah. This tape it normally comes in long bands, and you stick it on your skin when you have when you damage a joint, basically. So, for example, if you dislocate your shoulder, you would put it on the shoulder to maintain it. It has this interesting property that it's stretchable in one direction, but not in the other. And normally it comes with a beautiful white paper on the back, but this one we dyed it, or we functionalized it with our polymerization. And at the end, the paper is kind of dark, but it's still intact. So as you imagine, if you stick it on the skin, it has some kind of glue on one side, and it's just some classic textile on the other side. So in this case, what we're seeing on the screen, we're not using the stretchability yet, but we'll show another one later. What is interesting here is that we use the finger as analog input. I don't know if you see with your screen, but there is a little ring made of copper connected to a cable that goes to an Arduino. It goes to the analog input. And then on the two ends of the kinesio tape stuck on the hand, on the left hand of our test subject, we have this thing that is basically behaving a bit like a linear slider. It's a potentiometer. And so the hand comes, and by getting close to the red, you would get something that is close to the voltage input at the red crocodile clip. So this gives 5 volts. And oops. And on the other side, it's ground. So when you are close to the red, you have 5, and when you're close to the black, you have something like 0, or something between 5 and 0. And we can see the visualization that shows how to estimate the position according to this voltage. Super simple processing sketch. Again, it's available. Yeah, basically how to make a human potentiometer. But we'll show some other application. So after those small embedded applications that we just saw, one might wonder how scalable is this process? So this installation uses several meters of this textile. I think the light is not amazing, but actually you can see probably. So this is a polyester textile that's somehow replicating silk. We functionalized it after doing a kind of shibori technique. Yeah. And then after functionalizing it, it was not so red anymore. Originally it was red. And then it became very dark where we functionalized it. And then we pleated it. I don't know if it's visible, but it has this interesting kind of squishy, folded structure that creates an amazing passive haptic feedback. This other application is basically functionalizing feathers. And so in the previous example, we were doing artistic visualizations, not with shaders, but almost. And in this case, it's only sonification. So when you touch a feather, it's behaving like capacitive sensor. So a bit like the sensors in our screens of our phones. It detects that you touch it. And you can use it with an Arduino to trigger sounds. And that's basically what happens. This example shows that you can functionalize other things than textile. We tried, and most of the things that are porous or fibrous, they should work, except when they are very synthetic, like a piece of very thick synthetic textile usually doesn't work well. Anyway, you might recognize Hannah Perner-Wilson. So just after ITP camp last year, we went to this conference in Germany called CCC. It's the biggest hackerspace conference in the world. 18,000 people in the winter, and in the summer it's every 4 years, so it's smaller. And I think it was 5,000 people or something. So it's a big thing. It's really worth it if you have the opportunity. It's actually difficult to get the tickets, but it's worth fighting. Anyway, Hannah was showing her slides by folding her knees. You can see now. So we functionalized this pant and with some connections to not an Arduino in this case, kind of Arduino, but no. It's called XIO. It's another kind of board. You can send OSC signals and use them for changing your slides or visualization or whatever. It was really warm. and we realized, kind of with a lot of stress, thank you for the links, and basically the humidity of sweat is changing the values that you read. So you have to think about it when you make your own sensor, if you make it wearable. We didn't know at the time, so we discovered that it's a great humidity sensor. We discovered that painfully. And on the other funky applications, we realized that you can also warm or you can heat your user by putting electricity on the textile. So in this case, it's basically as anything resistive. If you put electricity, it will heat because it doesn't conduct very well. So it heats, and when you stop heating it, you can do that. You can alternate very fast. The same connection can be used to measure the resistance after you heat it. And it happens that the resistance changes with the temperature. So you can actually use it as a temperature sensor too. You don't even have to heat it, but it's interesting because if you heat your user, you can avoid burning him or her or them. As you can see here, we have some smoke, and it goes pretty fast if you put a lot of current. So if you want to make something for burning mine and make it burn perfect, it works really well. We had a few go on flames. You can see with this infrared visualization that it goes fairly hot. And we characterize the temperature versus resistance. So we can create this kind of, it's called PID. It's a loop that allows, a bit like your thermostat at home, it allows regulating the energy that you send to your heater to keep it at a regular temperature. So yeah, it's good if you don't want your user to go, to be put on fire. Quite nice. Here it's a little zip that was white originally, a zipper. So if you measure the resistance between those two sides, you have this kind of constant resistor that is, I forgot the value, something like 400K, 600K, something like that. And this is metal. So when you close it, you shorten the path of the electricity, and you get this kind of linear slider or potentiometer. So you can use it as a, let's say if you're in this kind of music application, you can use it as a, how would I say it? Like a potentiometer that can keep its position. Whereas the normal pressure sensor are more like for, let's say, wah-wah effect, or this one would be more like you change the volume, or you change a control signal that would be more about being stable. So this is an off-the-shelf zipper that just was white, made out of cotton, and they all work. One trick, if you do your own, is that the second step of the polymerization is oxidizing the metal, so you need to clean it after the process with flux, and maybe if you have a heat gun, it helps also to dissipate the flux. So we saw a few polymerization that we deployed in various festivals and conferences. Now you might want to know how to make your own. We have this publication that describes all the steps, but let's do a step-by-step together. So in our case, we use the washing machine to make a lot, but as I was saying earlier, you can do with small mixing things by hand. Hannah did a lot of this by hand. She was not really a fan of the washing machine. She's kind of a warrior, whatever. She doesn't give a shit. So first you put the water, and you should use a bit less than twice the amount of fabric that you're going to need. Knowing that the thing will move around, and it's nice if you have a bit more, but a bit less than twice, something between 1.5 and 2 times. Just soak the whole thing and a bit more, but just the water at first. That's important. Then you put the monomer. So in our case, it's pyrrole. I'll include links to buy the thing if you want. So this is a bit toxic before it reacts with the second chemical product. It's not super toxic. It's a bit similar to if you're using like a strong alcohol for like, I don't know, like cleaning stuff, or you don't want to put it in your eyes, you don't want to drink it, put it on your mouth. It's not nice. It stinks. Yeah. So in our case, we use gloves and goggles and even masks to avoid breathing shit. But I do that fairly often in the kitchen or in my hackerspace. It's fine. Once you have this mix, then you can add the textile. You soak it for like 10 minutes. And we could call that a kind of monomerization, which is basically bringing all of those monomer, those little chemical particles everywhere in the fiber. And then you add the oxidizing agent, which will trigger the polymerization. So again, it's iron chloride. In our case, it comes as kind of powder or kind of crystals. You break them and you dissolve them, and then you mix it. Again, this is kind of toxic alone. It would etch metal, is not super nice on your skin. At the end, if you put it on your skin, which I did many times, you feel like super dry hands. So it's not super toxic, but it's not super nice. So that will trigger what is called the Insitu Polymerization. I'll explain that a little bit. But concretely, if you want to make piezoresistive sensors, so the one that measure the pressure, about half an hour works most of the time, maybe 45 minutes for synthetic materials. If you want to make capacitive sensors, as the big one that I was showing earlier, that was like several meters, 2 hours is really the minimum for capacitive sensors. In our case, we were making several meters, several yards of this textile. I forgot, it was maybe 6 by 10 or something like that. And we folded it, so it's not obvious, but it's actually a lot of textile. And we did several machines of this, several nights. Yeah, every time one night of polymerization. But basically, the longer you polymerize, the better the conductance will be. Yeah, polymers are chains of monomers. So the monomer is what we see on the left. It's just one element called pyrrole in our case. And the polymer is a long chain. Here we just show 4 of them, but it's really long. The chains of monomers that are built around each fibers, almost like if they were merged with the fiber. So it's more than a coating. I like to call that a bit like a molecular level dyeing, but you can imagine that the fiber itself becomes conductive. And this is called in situ polymerization because the monomer is already everywhere around the fiber, already soaked in the fiber somehow. And when you trigger the polymerization, it will connect with all of its friends and create those conductive particles that are very long. And this is the trick. We tried so many approaches and we couldn't imagine that first there was this thing, pyrrole, that existed, we didn't even know. But the way of making it in 2 steps like that is the technique. So if there's something that you have to remember in this process is that it's in situ and it's this 2-step process that creates those conductive chains. So this polymerization is mostly creates chains of carbons at the end, and they're actually not toxic. We did some tests with the material science lab, and the technical way of doing is that you take some skin cells that are still alive and you mix them with the result of the polymerization. And if they are still alive 24 hours later, it's considered as non-toxic. And this is fine. They did this process for another application, which is basically using these functionalized materials as what they call textile batteries. So what they do is they use another layer of another chemical and they put it underneath the armpit, and they use the sweat to generate a chemical reaction which creates energy. So it's not exactly a battery. I would say it's more harvesting energy, but in a way it's also a battery because it's maybe etching a little bit some part of the materials. It's not an infinite generator. So we create these chains of carbons, which explains why the result is so dark. But it also explains the electrical conductance because the carbon chains are fairly conductive. So I think this might knock out a few people here, and I will probably skip most of it. But what we did is, as a scientific team, we had to characterize it. So we did different tests, basically measuring 3 pressures that we can see here over time. And so we measured the pressure with a Newton meter, and we measured the resistance. And so we did 3 pressures that we can see the 3 peaks here. And we looked at the memory effect because some pressure sensor would stop working over time. And so some of the materials would not work as well over time. And it's normal. We have to find the right materials. For example, felt has this natural way of bouncing, but other materials don't have that. The stretch sensor is, the stretch textile is, Lycra, for example, is quite nice. But some like t-shirts don't have this very good behavior over time. So we characterized these, and we found that we actually have a better range of resistance in different cases. So the non-woven felt, the paper, strangely has a nice, so it's not, it has a nice behavior. This one is just a sweatshirt fabric. This one is interesting because it has a high resistance, which makes that the sensor uses less electricity to work. So there's a question: does overtime take into account like the accumulation of body oils and washing? That's a very good point. We'll talk about that a bit later, but indeed we have to wash the materials so they are not fat before. Otherwise, if there is any fat like oil on the textile, the polymerization won't work. In a normal scientific lab, they would use ultraviolet to clean the materials before also. Alcohol also. So if you want to improve your material, you can do it with pure water that was distilled. And those processes that I just mentioned, like UV and alcohol.
I think he's asking about the degradation over time.
So the degradation over time can be stabilized. So if you wash it a few times, I think it was something between 5 and 10 times, there's a moment when, so it will decrease the behavior, but over time, after a certain amount of washing, it will stabilize. Now, oil, I haven't tried, but we tried attacking the textile with UV, like sun exposure. And again, there's that, like a kind of a preparation. So you have to attack it with UV, and then it stabilizes, and then you can release it to your customers if you want to sell it.
Also, the museum exhibit was a lot of human oil.
That's true. That's true. So I guess human oils didn't really affect it so much. Pre-shrunk t-shirts. I'm not sure what you mean. Like examples of materials that we could use, yes. Yes, pre-washed jeans. So jeans would not be very pressure sensitive or stretch sensitive. But I guess, yes, if you take it in diagonal, it could. Anyway, so I won't go too much in the details of those characterizations. If you're interested, feel free to ask me more questions. let's talk about design methods, because I think it's the most interesting part for craft making. Last question. The same process of having to treat the material so that the fabric is stable between washes. Yes, that's the idea. I guess when you buy a textile that is already dyed, like probably this, it was pre-processed before it was released. That makes sense. Yeah. So this is the same idea. So we made this interesting way of giving a functionality, an electrical functionality to fabric. And it's already amazing. But we just replicated mostly what exists, what is made by Eonix and other people also by Velostar sometimes, which I don't think is as good as the Eonix. I think Eonix is really the best in the industry, except our material. But you could say, all right, it's a bit like copper. So those are blank PCB materials. Copper is great for electronics, but it's better when you give it a structure. Like you can create circuits, or in our case, we can even create sensitive parts in the circuit. So we look at the possibilities, and we were inspired by traditional techniques such as shibori here, so kind of a tie-dye traditional technique from Japan. It's interesting because it allows very simple ways of hiding the textile from the polymer. And you can see the white part here is not functionalized, and the black part has this superpower of conducting electricity. But we can also make gradients, as you can see. It's kind of nice. So we characterized it again. I won't go in the details of that. But yeah, you can see a little bit the gradient at the top right. Another interesting traditional technique called ikat, also from Indonesia. We'll see another one from Indonesia afterward. Is interesting because you can functionalize just fibers, and there are some. Let's see this. Some people. This one is called Project Hilo in Berlin, who found a very smart technique to use this kind of mix of fabric that is functionalized, or let's say just dark or white, and you can, if you have a machine that spins textile, you can have, for example, a white core and a black thread that rotates around it, that is spun around it. And if you densify the black thread, you can have dark areas. And if you don't densify, you can have mostly white areas. And if you do that in a smart way, you can anticipate where you should have dense areas or where you should not. And imagine this picture here. You can see it as a thread in the raster order. So this zigzag shows it. And you can say, I want this zone to be dark, this zone to be dark, and so on. And you can create this triangle, for example. So they created this software that allows making your own thread and controlling a weaving machine so that you can create patterns. And you could create functionalized patterns. So we tried different fibers like linen, silk, and a few others that work really well. But it's not super easy to functionalize. So you need some tricks, some techniques to make it without the dreadlocks, because then your fiber is messed up. It's kind of a mess. But yeah, we worked with those guys. Project Hilo is the full name if you are interested online. They have Studio Hilo, the website. Another interesting technique from Indonesia called batik basically uses wax to mask the polymerization. And this wax can be removed afterward. So you can do several steps of functionalization. So we did some simple tests with this kind of zigzag and looked at how the conductance works between 2 points and how it's isolated between 2 areas that should not be connected. And we can see that we have megaohms. We really didn't do that very cleanly, but when you have megaohms, it's pretty much isolated. Whereas if you have 2 zones that are in the same area, like M2, they are kind of conductive, so you can use that part as a sensor. Question?
2 questions. The first one is, what is the difference between Eonix and Velostat? What makes it better?
So Velostat is not textile. It's a plastic that happens to have this high conductance. I think it's originally made for electrostatic dissipation or isolation. So it's basically conducting electricity, but not very well.
Then, do some fibers totally reject polymerization? I guess like hair.
Oh wait, just so the other the Eonix is really nice. Just to finish the difference, the Eonix is really nice because it has this. So they have 2 main kinds of textiles. One is stretchable, which is also pressure sensitive, but not as nice. The other is woven. So the first is kind of lycra, and the other is woven. Sorry, non-woven. It's like felt, and it has this nice Z pressure behavior. It's kind of bouncing like foam. And they have nice range of resistance, better range than Velostat. And Velostat, as it's not textile, if you wear it, it's really like wearing plastic. You don't really want that. Sorry, second question?
Do some fibers totally reject polymerization?
Yes, so some polyesters really don't like polymerization. We tried a few. I'll share some more details if you're interested. Yeah, feel free to ping me. But yes, so you always have to try a few samples at the beginning, and then you see what works, and you see how long each material needs. But usually it's something between 30 minutes and 45, 60 minutes. If it doesn't work after 60 minutes, it's unlikely that it will work. And you can see it visually. If you start from a white material, it should become almost black or dark gray. One more question.
I don't totally understand what you use Studio Hilo to do.
So we actually haven't, this is a work in progress. We haven't done yet. So the Studio Hilo allows basically making patterns of woven textiles that have either functional or non-functional fabric. And for example, here you can imagine this triangle could be a pressure sensor or a capacitive sensor, but you can make any kind of shape. So we saw with shibori or batik that you can make fairly random kinds of shapes. But if you want to make it in a scalable way, you could also have that kind of approach where you would prepare your fiber in advance, and then you weave it with giant machines that do it really fast and really well. So I think I was here. This is a little bit outside of the functionalization that we're talking about, but this is still a cool trick. If you take the classic copper textile that you can buy, which is usually made for isolating like electromagnetic wave, you can find that on lessemf.com, I think, .net.com, lessemf. People who want to isolate electromagnetic frequencies. So this textile is pretty much copper on top of polyester, and you can etch it the same way as you would etch a normal PCB. So in our case, we used iron clay. And we found that if you do that, you can create circuits, and once you have your electrical circuit, then you can add the functional, the sensitive part. I see that I speak a lot, so I'm going to go fast. In this case, it's a quick It's a simple stretch sensor. So if you stretch horizontally, this resistor will change, and if you stretch vertically, the other one does. Here we did a pressure sensor, which is somehow taking advantage of the fact that you can fold your circuit. That is a kind of hybrid circuit. So it has this conductive part that will come in contact with this C zone, and then if you fold it again, this other conductive part will be on the other side. So you have this sandwich that is entirely made of textile that is folded with the conductive and the piezoresistive part. You can make a pressure sensor. So we looked at the microscope results, but I will skip that. It's just to say that some parts really functionalize well and the synthetic don't. We can talk about that more. Some of the philosophical takeaway from this project is I didn't have the background to understand how to do this kind of functionalization, and I've been just asking many people in hackerspaces, people in academic conferences, and basically this one was not possible if I didn't ask people in a conference who told me, hey, yeah, I know someone who does material science, they can help you. This is a quote from Irene, another friend from the Irene Posch from the e-textile community, who said in a TI paper, if you can't, no, sorry, this one is, my bad. This one is from me. If you can't open it, you don't own it. Again, this is about this open source movement. I will go fast. And that's the quote from Irene, my bad. Tools and materials are never neutral. And this is fairly obvious when you look at those machines, let's say for people who make music, like a Pro Tools setup costs a lot of money, whereas open source tools can do the same. If you look at scientific tools like, embroidery machine, right now, you should look at on Twitter, this guy called Golan Levin. He's a guy from the processing community and open frameworks. He's been making an embroidery software that allows you to make custom shapes from processing. The normal tools cost thousands to make custom patterns, and he's basically making it open source and accessible. And so if you make tools that are closed sources, not everyone can use it. And so this is not neutral in that way. So I'm so sorry I speak too much. Now it's going to be Olivia showing a little application that we did together. Do you want to share your screen? Isn't it more particular? You're fine?
I think it's faster. We don't have a lot of time, like
okay.
3 minutes.
Okay.
so just really quickly, what we did with the,
the GIF doesn't work?
That's fine.
Should I show?
I think people are going to leave for the other session.
Okay.
So basically what we did was we attached the stretch sensor to an Arduino, and then when I move my hand up and down, the Perlin noise visualization will move accordingly.
So this sensor.
And so the information pipeline, how that works is we take the analog signals from the textile, we read it through an Arduino that I'm actually holding in my hand in the GIF, but you can attach it in another form if you prefer. And those signals are connected via serial port to a app running Node.js on my computer, which then converts those into something that can be read via WebSocket into P5.js, and that will control this. And you can see that GIF moving over here. What you would see with the whole system set up is this Perlin noise visualization actually moving like waves, and you can check it out at this link. I'll send it in the chat later.
I can also show a GIF somewhere else. I think I have it somewhere else.
Okay, I think you actually had it in your presentation.
Yeah, exactly. I'll show it afterward.
An alternative to this that bypasses this P5 serial control app would be just to use something called Web USB. And one of our friends created a tutorial that you can check out later if you're interested to basically skip from using the Arduino to getting the signals read in P5.
Yeah, it's quite nice. You can go faster and avoid this step. But it has this little problem is that not every kind of Arduino works. You have to use an Arduino Leonardo or this kind of Arduinos, or those Arduino Zero, those that allow you to configure the processor as a, you can, those that have a real hard USB hardware, basically. So not the Arduino Uno, for example. I think I have, the GIF is here. This is the visualization. So basically, the stretch changes the angle of the orientation of the Perlin noise. And Olivia just sent the link. So the link will be a bit disappointing because you don't have the sensor connected, so it's not moving. But you can use an Arduino and a bit of P5 to play with it. It's noon. I'm happy to leave you alone and take your question if you have any.
This is PolySense, reverse engineering flex sensors and destroying your kitchen with chemistry for electrical functionalization of everyday objects. Cedric Honnet, thank you very much for joining us today.
Thank you.
And, we will have time for just a couple of audience questions, maybe one or two. One member of the audience asked about the washability of this material.
So I somehow replied on the Riot channel. I think the way, the simplest answer is that when you make your own material, you have to wash it at the end because there's still a lot of chemicals which are not too toxic at the end. But you still need to wash them, otherwise you get some kind of gray powder on your hands. And I usually wash them like 5 to 10 times, something like that, after functionalizing the material, and then it gets stable. So it's fairly reasonable after that. Obviously, if you wash it 1,000 times, super hot and so on, it will damage it over time, but it's reasonably stable otherwise.
Thank you. We have a question from the audience asking, can you obtain the heating effect at a lower voltage? I'm thinking of the concept of plugging in a USB power bank on a cold day to heat clothing.
So that's a very useful feature indeed. I would say that if you have a power bank that can provide a reasonably good amount of current, which is the case in general, depending on the way you organize your polymerized circuit, it can have, for example, a long path that has a lot of zigzags, or it can be just a one big pad. So depending on the structure, you can adapt the resistance of the system and allows it to work with a lower voltage, but it will consume more current. It has to be somehow proportional, right? So it's possible. It would need some test. I haven't tested that yet. But I like it.
And we'll have to leave it there because we're just about out of time. But very quickly, Cedric, where can people find more information about your work and get in contact with you?
I can send this link somewhere, everywhere. The simplest is Counter Chemists on GitHub. So if you look counterchemist.github.io, there's all the documentation. If you look up also PolySense on Hackaday, we have a good documentation there. I think those are good starting points.
Excellent. Cedric Honnet, thank you very much for joining us today at Hope.
Thanks to you.
And just one more quick announcement for attendees watching. You're invited to take the Hope stage yourself at 1500 EDT this afternoon. You have up to 5 minutes and up to 5 slides to share knowledge of interest in our lightning talk session. Go to the Hope Announcements channel on Matrix just before the start of the session to get the meeting link and give your talk in our lightning talks. No pre-registration is needed. Cedric, thank you very much indeed once again for joining us today at Hope.
Thank you.
We'll throw it right back to ground control.